Okay, class. Today we're learning about proofs by contradiction. Very weird sounding thing. We haven't talked about contradictions yet, so that's a good place to start. Before we move on to what the section is really about. So a statement is called a contradiction if, well, you probably have an idea about what the word contradiction means, if it's always false. So you can, of course, just say something that's false, but this is more with regards to putting together a bunch of statements with a bunch of logical operators and then seeing that the result is always false no matter what the building blocks of the statement are. So for example, if I say P and not P, this statement is always false. Because it's an and statement, it's only true when both are true. But P cannot be true when not P is true. Just by definition, when one is true, the other is not true, and vice versa. So that means that they can never both be true. And so that means the and statement combining them, this guy, is always going to be false. Okay, so that's what a contradiction is. We're not going to talk too much about things like this, where you can just string a bunch of statements together and make contradictions pop out. But I'll give you one specific example. So if I said like x is even and x is odd, that would be an example of this statement. Something and something else that both cannot happen at the same time. So rather than spending too much time on contradictions themselves, we are going to do something else. We use contradictions to our advantage. Sounds interesting, and it really is. So far, this will be the most interesting thing we've studied, I think, is this idea of proving something using a contradiction. Okay, so here's how it's done. So let's just think about your classic if-then statement. So because these are things that we're often trying to prove. We're trying to prove like if blank happens, then blank happens. So we're often looking at things like this, so it's a good place to start. So here's one fact you can already say. It's either true or false. There's no in between. And that creates something really cool, because what we can do is we can pretend it's false. It doesn't hurt to pretend. In fact, it's fun. So we can pretend it's false. Why the heck not? But what will happen is if it's actually true and we did this, so we don't know it's true yet, but if it is actually true, then not always, but likely, pretending that it's false will lead to a contradiction. So what does that mean? Well, that means that it couldn't possibly have been false. Why not? Well, because if it was false, then it leads to some weird contradiction. And there are no contradictions in math. So that means that it can't be false. And if it's not false, then what does it have to be? It's got to be true. So this is a proof that it's true, following this logic. Okay, so let me just re-summarize it. If you have an if-then statement, it's either true or false. And you can pretend it's false and do a bunch of stuff assuming it that it's false. But then you hopefully will run into a contradictory thing. So something like 0 equals 5. That's a contradiction. That's a false statement. That's always false. Or you might run into something like x is even and x is odd. So then what you're saying is, if I live in a world where this guy is false, then in that world, x is even and x is odd. But that's impossible. I don't live in such a world. Therefore, there's no way this thing could be false. Because again, if it was false, I would live in a contradictory world. Therefore, if it's not false, well, it's got to be true. That's the only other option. So that's the logic behind proving something by contradiction. Okay, so the contradiction aspect really just comes towards the end of these proofs. The more important thing that we're using about logic is that things are either true or false. Okay, so let's go ahead and do an example of a proof like this, just to see how it works. So here's a statement, and I'll do an if-then statement, although afterwards we'll see other types. So if x and y are real numbers, so just any old number that you can possibly imagine except imaginary numbers, because you can't imagine those, and x does not equal y, and x is bigger than 0, and y is bigger than 0. So you have all of this stuff being assumed in the if portion. Then this weird thing will happen. X over y plus y over x will be bigger than 2. Okay, so just sort of a weird random statement. We haven't seen things like this too much, but it's good for an example of proof by contradiction. Okay, so this case we already know we're going to do a proof by contradiction. So I'm going to start by saying that, but oftentimes you would figure that out in the scratch work. So you might say something like proof, and then in parentheses, by contradiction, just so that the reader knows that it's a proof by contradiction. Okay, so what we're going to do is we're going to assume that this statement is false. But let's think about that before we do it. So if I'm assuming that this guy is false, what does that really mean? When is an if-then statement false? It means P is true, but Q is false. So what I'm really doing is I'm assuming that the if part still happens just like I normally would in a direct proof, but I'm pretending that the Q part, the conclusion, does not follow, that it's false. So that is one way to think about proofs by contradictions, is you're just letting the if part still be true, but then you're also letting the Q part be false instead of trying to show that it's true. Okay, so let x and y be real numbers where x is not the same as y, x is bigger than 0, and y is bigger than 0. And instead of trying to show the conclusion, that's what you would normally do, we're not doing that this time. We're doing a proof by contradiction. So we're not going to say that we're going to show that, because that's not what we're doing. Well, I guess we are. We're showing it's true by doing this roundabout thing. But because I'm not directly showing that it's true, I'm not going to write that down. Instead, what I'm gonna assume is that this thing is false. And what people like to do is, if they know they're doing a proof by contradiction, they write something like assume to the contrary that, and then they write the conclusion is false. So what does it mean for this guy to be false? So let's think about that real quick on the side for some scratch work. So this being false, because it's a greater than, that just means that instead of being bigger than 2, it's going to be less than or equal to 2. So that's the negation of that concluding statement. So because we're assuming that the conclusion is false, what we're really doing is we're writing the negation of it. So what people do is they write in the proof something like assume to the contrary that x over y plus y over x is greater than 2. Sorry, not greater than. I just said what I was going to do and I didn't do it. Less than or equal to 2. And then if you want to be very explicit, you can write more things like what you're going to do now. So you can say, we'll show, what are we really trying to show? Well, in a proof by contradiction, we're trying to show that by assuming the conclusion to be false, that the result is a contradiction. So you can say, we'll show this results in a contradiction. Now, this is where the main difficulty comes from in these types of proofs. And this is where it's way different from a direct proof. So normally, in a direct proof, you have some sort of goal that you're trying to get to. But here, the goal is sort of just anything that doesn't make sense. And so you don't know where you're going until you get there in these situations very often. All you do is expand upon your assumptions. So all we're going to do, we're just going to expand upon assumptions. Notice we have additional assumptions because we're not just assuming the if part like we normally do, we're also assuming that the then part is false. So we get to say extra things are true because we're assuming the conclusion is false, is really just saying we're assuming the negation of the conclusion is true. So we still are assuming something is true, and that is that this happens. And so we're assuming that that this is true so we can use it somehow, along with the stuff we assumed that was in the hypothesis, all of this. Okay, so we're just going to expand upon assumptions and then see if something goes wrong. Something is going to go horribly wrong. But from our perspective, it's horribly right because it's going to mean our proof is done. Okay, so what kinds of things do I have to work with? All I have to work with are that x and y don't equal each other, that they're both positive, and this little inequality here. Well, why don't I just try playing around with this inequality that is supposedly true now? Because again, I assumed that this inequality up here was false, but that just means I'm assuming this one is true. Okay, so I'm going to play around with it. So we can say, so why don't I get a common denominator between the fractions so that I can put them together and just see what happens. So this is something that you would try in Scratchwork before writing down in your proof. Okay, so this follows from that thing in the square here, this blue guy, that just follows from that. Let's keep playing around with it. Why don't we multiply the xy over? Now, really quickly, why am I allowed to do this? Because you might remember something about inequalities, which is that if you multiply by a negative number, it'll flip the inequality around. Why doesn't this inequality flip around, or why do I not know if it does or not? Well, it's because x and y are both positive numbers. So this is okay to do only because x and y are both positive numbers. So when I multiply their product across, it's not going to flip the sign. It's going to keep it exactly the same. All right, so then all I'm doing is sort of playing around with this guy. And what I'm going to do next is I'm going to subtract the 2xy over, and I'm going to stick it in the middle here. And you might see what you can do now. So these steps are sort of, again, these would be things you're figuring out on the side. These are like, well, why would you do that? Well, I don't know why I'm doing that. It's because I'm hoping something will go wrong, that I'll get something that doesn't make sense. But I'm only allowed to do steps that do make sense. I can't just like stick numbers wherever I want. I have to like do correct rules. But I'm hoping that by doing these correct rules, I'll lead to something that doesn't make sense, and I will. And here's where it happens. If you remember some algebra, you'll remember that I can factor this as x minus y squared. So this is a bit weird because this is saying that I have a square which is less than or equal to 0. But if you square a number, it has to be positive, or at best it could be 0. So really this cannot be less than 0 ever. It can only be equal to 0 because it's a square. Okay, so then what is this saying? Well, if I want to, I can think about it as square rooting both sides, but really what this is saying is that x equals y. So this is the contradictory statement. I'm at the contradiction. Why am I at the contradiction? It's because, what else have I said a long, long time ago? I'll put it in red since it's bad. That fact, that assumption that x does not equal y is in direct contradiction with this. So that's what you say. You say the contradiction. This contradicts that x does not equal y. So this is another spot that students get very tricked by, and it's because, well, you just need more practice, but here's what's tricky about it. So when you get to the contradiction, what do you get to say afterwards? Well, the contradiction was just the end of the road, but you have to go back to the beginning of the road to see where you took the wrong turn. So the wrong turn was this guy in blue. Assuming that is what led me down this horrible path where I got a contradiction. So what you say next is always that is what was incorrect. You don't say anything about the things that were contradictory. So here's what people write. A lot of times that's wrong. They'll say something like, therefore x equals y, because they'll look at the contradictory statement and try to pick something out of that. But that's not what's going on. What's going on is that the thing that we assumed false is what broke mathematics. So therefore, this thing is what's false. So we assumed it to be true, and that is what broke math. So therefore, it can't possibly be true. It has to be false. More generally, what we did was we assumed P implies Q is false. And that more general assumption is also, you can think about it as what broke math. So what you can say is that this whole statement could not possibly be false, because if it were false, this blue thing would be true, which is now, I guess, white. And if that blue thing were true, white thing were true, then you would get this contradictory, these contradictory statements happening at the same time. Okay, so what you say is that the thing you assumed true is actually false. Thus, what's true is its negation, the thing that we wanted to prove, which is this is the guy that we wanted to show is true. And we have shown it's true by showing that it's not false. Because if it were false, then this guy would be true, but it's not. It's false. Okay, so thus this guy is true. So the statement is true. Okay, so this is how it works if it's an if-then statement. This is the basic outline. You start off by, as before, assuming the if part is true, but you assume the conclusion is false, which tells you something else is true, that's this. Then you work with that being true until you get to a contradictory statement. Then you go back to the beginning of the bad road and you say, okay, that was actually false. Therefore, the thing I wanted to show was true is actually true. And that tells you the whole statement is true. Okay, because you've showed that P, if P is true, then so is Q. All right, very neat idea. And I guess I said all the steps, but I just do want to write them down just so it's there. Let me do it one more time then. In general, for an if-then statement, what you really do is assume Q is false. And what that's really doing is you're assuming that the whole thing is false. But in the proof, the extra piece that you're doing is you're assuming Q is false because you already were going to assume P was true, which is how you make P implies Q false. So you assume Q is false, get to a contradiction, and then you get to conclude that Q is true because it had to have been true. Otherwise, if it's false, you live in this world that doesn't make sense. And then this is exactly what shows that this whole thing is true. Okay, those are the steps. Now, a statement doesn't have to be in the form of if-then, but it's easiest if it is. So for example, I can have something like this. For any x comma y in the real numbers, if x is between 0 and 1, so some sort of fractional number between 0 and 1, that's one way to think about it, then this will happen. If I do 1 divided by x times 1 minus x, that'll always be bigger than or equal to 4. Okay, another sort of weird, just random statement. So this one is a little bit annoying because it's got the for all in front of the if-then. So we do have to sort of think about it. But one thing you could do is you could rewrite it just as if P then Q and stick the for all in there correctly and then do what we just did above. But let's try to keep it like this for this, just to see how it works. Okay, so now it's not an if P then Q, it's a for all. So it's a for all x comma y in something, P implies Q. Well, I'll call it P of X, because it depends on X, implies Q of X. So if I want to do a proof by contradiction, I have to start off by assuming this is false. And that just means we assume the negation is true. Same exact thing. So I can look at the negation of this guy. And then I have to remember those rules. So the negation turns the for all into a there exists, such that, and then it passes through to the predicates. And now I'm sort of back to the previous part, the previous example, in that all I'm really doing now is I'm just saying that the if then part is false. And that comes down to doing the same thing as before, meaning assume that the Q part is false, but P is true. And so that's all the same with this little extra caveat that I'm gonna also suppose that there exists such a pair of numbers doing this stuff. That's how my proof is gonna look. Okay, so that's the generic idea. So let's go ahead and try to prove it by actually applying all this logic to the statement we're in. So what we're actually saying is that there exists an XY, sorry, this is what we're gonna assume to the contrary, that there exists an X and Y in the real numbers such that P of X is true, so this stuff still happens, such that 0 is less than X is less than 1, but I want Q of X to be false, such that that happens, such that, sorry, I forgot the if. If that happens, then Q of X does not happen. So what does it mean for this thing to not happen? Because it's an inequality, it just means to flip the inequality. And because it has an equal sign, I get rid of the equal sign. So this is really what I'm assuming to be true. So when I actually start writing the proof, my proof is going to start off by saying all of this stuff is true. Okay. Oh wait, why did I have two numbers? Ugh, there's no Y in this crap. Why did I do that in the first place? Okay, get rid of that Y the whole time. I don't know why I did that. Why not? Okay, so there was no Y's. Luckily, I didn't use them anyway, so I didn't put them in the P of X or Q of X. Okay, let me just get rid of all these Y's real quick. Okay, so let's do the proof. So what I've done so far is just figured out what I'm going to be assuming is true. So I'm assuming all of this happens. So it's a bit weird to put this if here. It sounds a bit weird, and this then sound a bit weird. What I'm really doing is I'm assuming that there's going to be a real number which is between 0 and 1, because I'm assuming that it exists, and it obeys this property on the right there. Okay, so assume that X is a real number where it is between 0 and 1, and this happens to it. So I want to do some stuff and arrive to a contradiction. So what can I do? Well, again, on the side is where you would be like playing around with this stuff. So you might think, okay, I can look at this thing again, just like I did before, sort of on the previous example. I looked at the inequality and I just played around with it. So maybe I'll multiply that guy over and see where that goes. But you do have to justify why this is okay and why the inequality stays the same way. So that means you have to think about, why is x times 1 minus x a positive number? Otherwise, if it was negative, it would flip it. And it is positive. So since 0 is between x is between 0 and 1, this means, so it's like some fraction, like a half or something, or a third. So if I do 1 minus x, that's still going to be a positive number, because I'm not subtracting anything as big as 1, so I'm staying in fraction land between 0 and 1. So that's why that's true. So that means if I just multiply by x, which is also a positive number, a positive times a positive is positive, so that'll still be positive. So yes, I can multiply that guy across up there and not worry about the inequality changing directions. Okay, so now I'm back to just, let's just like play around and see what happens. So maybe I'll distribute that through. And then maybe I'll get everything to one side. This is stuff that you would do as scratch work and just sort of hope that it works. Oops. Hope that it leads to a contradiction. And it's good to get 0 on one side, because 0 is like the number that you can compare against most easily, because you can think about this as saying, this is saying that the left side is always negative. Well, maybe I can factor it like I did in the previous problem, and in fact I can. This becomes 2x minus 1 squared. And this is a contradiction, because this will never be 0. Or it'll be never less than 0. It won't even be equal to 0. This is a contradiction because 2x minus 1, well, x is just going to be between 0 and 1. So this guy can never be equal to a negative number if I square it. This is true instead. Right, so if you want, you could like plug in 0 and see that this happens. So like if I plug in 0 for x, x can't be 0, but that's like the lowest it can go towards. So if I plug in 0, it won't get to 0. And if I plug in 1, I'll get 1. So I'll just never be 0. Okay. So this is the contradiction. These two things. But what does that mean you do? So this means not anything to do with that stuff. That was just a logical conclusion of our mistake, which is assuming that our original statement was false. So what we've done is we've shown that this guy cannot possibly be false, or else you get something impossible. So it's true. So this means our assumption was false, so the actual statement which is not what I was assuming to be true. That wouldn't make sense. I'm not going to assume something true is true. I'm going to assume something false is true to get to the contradictions. Whoops, I wrote the word assumptions because I was saying it too much. Okay, for all x in the real numbers, if 0 is less than x is less than 1, then 1 over x times 1 minus x is bigger than or equal to 4. Okay, so because I'm assuming a for all statement is false, is a little bit different than last time. I'm just going to write down the whole thing that I was trying to show is true. Okay, so our assumption was false. That means what I'm saying there is this whole thing we assumed to be true was actually false. All right, so that's the end of the proof because that proves the statement. That is the statement. So this guy is true. So one little note. So if you have some statement that you don't know is true or false, so I don't know, let's just call it x. And you don't know it's true or false. You don't know yet. Well, if you try a proof by contradiction in this situation, what that means you're doing is, it means that you are going to assume x is false, and then you're going to try to get a contradiction. But if x actually was false, you would never get there, because you would be assuming a true statement. Because you're assuming not x is true, and it is true if x is false. So if x was false, this means you would be assuming a true statement. And if you assume a true statement is true that you don't actually know is true yet, but you've assumed it's true, you're never going to get to a contradiction because all you've done is say something that's true. So this will never lead to a contradiction. And so what could happen is you could just go on endlessly looking for a contradiction, but it'll never be there. And you'll never be sure that you're done looking because you don't know yet whether it's true or false. So you do have to be careful of this kind of stuff. What's going on in this class is I'm giving you statements that are true typically. So I'll say, this is a true statement, prove it's true. So then you're lucky because you can assume it's false and be confident that a contradiction will show up. But if I secretly gave you a false statement and I said, prove X is a true statement, then you would get stuck because you would assume it's false, and assuming it's false would not lead to a contradiction because it actually would be false. All right, but I'm not that mean, so I won't do that, I don't think. Let's see, I want to do another example. Let's do it. All right, here's another statement that will prove by contradiction. So it's another for all statement. This time it does have two variables. For any x and y in the integers, if x and y are odd, then this is a little bit different. Instead of saying there exists something, I'm going to say there does not exist an integer z such that x squared plus y squared equals z squared. Now, if you want to use fancy notation, you can. There does not exist. How would I write that? I can write it as a there exists symbol with a cross through it like that. But I haven't used that before, so I didn't want to start right there. Okay, so how would I do a proof by contradiction for this? I have to assume it's false, get to a bad thing. That's impossible. Okay, so in this situation, what I'm going to do is I'm going to convert it to an if-then, just to make my life easier, because I like those better. So as an if-then, how can I write this? This is really just saying, if x and y are odd integers, so this for all, I can just really get rid of it and stick it in here, and like keep it a secret. So if x and y are odd integers, then the rest. And it's saying the same thing. So for all statements can often be turned strictly into if-then statements very easily like this. If x and y are odd integers, then there does not exist an integer z such that x squared plus y squared equals z squared. So now if I'm going to do a proof by contradiction of this thing, I'm back in the other version where I just only have to worry about assuming q is also true as an extra piece. So that's how the proof will go. Proof by contradiction. So because it's an if-then, when I assume that this guy is false, I can skip ahead and realize that that always means just assume q is false as an extra. P is true, like always for any direct proof. But the difference is now for contradiction, I assume q is false. So if-thens are much easier to deal with. So it's nice if you can rewrite it as an if-then. Okay, so I'm going to assume this if part as always. So let x and y be odd integers and assume to the contrary of the conclusion that, so what's the contrary, what is the negation of there not existing an integer such that that happens? Well, it's that there does exist one. There does exist an integer z. So it's not like negating a there exists, which becomes a for all. When you negate a there does not exist, it's much easier. You just say, well, then there does exist, such that x squared plus y squared equals z squared. Okay, so now what we're trying to do is get to a contradiction. So we got to use our assumptions to write some stuff out and hope that something goes wrong. So all we know right now is that x and y are odd integers. So I can write x as 2 times something plus 1 and y as 2 times something plus 1. And then I know that there exists some z doing this, making this equation work. So why don't I calculate x squared and y squared and see what happens? Okay, so then since x and y are odd, I can say that x equals 2n plus 1 and y equals 2m plus 1 for some integers n and m. And then I can say that x squared plus y squared equals z squared becomes 2n plus 1 squared plus 2m plus 1 squared. Okay, and then I'll just keep going, so hope something goes wrong. So I'll square these and multiply it all out. So I get 4n squared plus 4n plus 1 plus 4m squared plus 4m plus 1 equals z squared. And then do some tricky stuff. So I'm going to factor a 2 out here. Oops, I guess I factored a 2, so that should be a 2 now. 2n squared plus 2n. 1 plus 1 gives me 2. So I'm factoring a 2 out of that, and then also out of these guys. So I end up with this. All said and done. What does this mean? So remember, I'm not trying to get anywhere. I'm just cruising down the road, down the open road of contradiction land, trying to find a contradiction, but I don't know what I'm looking for yet. So I'm just going to keep saying what's happening as I go. So this means that z squared is an even number because it looks like 2 times something. Okay, that's not necessarily a contradiction yet. There's nothing wrong with z squared being an even number. But here's an interesting thing. So notice z must also be even since z is an integer. So just a little side note here, what's going on. If you have a square that's even, so normally like you could say, oh, well, 14 is even, but z is the square root of 14 is not even. So normally you might say, just because z squared is even doesn't mean z is even. And that's true. But we already know that z was an integer to start with. And when that's the situation, then you can't have z being some square root of some weird number. So it has to be a situation like z squared is like 16 and z is 4. So more generally, z does have to be even. Okay, so that's just a little side mini proof of what I'm going to say next, or what I just did say. So z is also an even integer. So then z looks like 2 times some other number. And what I'm going to do next is I'm going to go back and replace z with this 2 times k. So I get 2 times 2n plus 2m, oops, sorry, 2n squared plus 2n plus 2m squared plus 2m plus 1 equals 2k squared. Aha, 4k squared if I do that. So then I'll divide out 2 on both sides, and I'll finally get a contradiction. Why is this a contradiction? Well, factor out a 2 on the left from just the first 4 terms. Oopsie, not like that. Like this. What is this saying? This is saying that an odd number equals an even number. So this is the contradiction finally. So what happened was we got to a contradiction by doing something wrong at the very beginning, which was what? By assuming that there existed some z fulfilling this equation. So that is what is wrong. Therefore, there does not exist a z such that x squared plus y squared equals z squared. This shows the proof. This shows the statement is true. So again, we're doing a lot of negations here, so you got to be a little bit careful. The statement, what do I mean by the statement? I mean the very original statement, not the negation. So I have just showed that this guy is true, which also means the original was 2. This is just a different way of writing it. So I showed that this was true by showing that it can't possibly be false. And that was done by showing that Q cannot possibly be false when P is true. So this leads to the contradiction. And because it can't possibly be false, it must be true. So going back up the chain, the very original statement must be true. One thing people do is they write this fancy symbol for when they do a proof by contradiction. They put 2 double arrowed implies facing each other. You could do that too. Little fun little trick. Okay, let's see. I think that's all. So if you want some extra practice, I did leave this space here because I was thinking I might do it. I was going to do it the other way. So I was just going to immediately assume that this was false. Instead of rewriting it and then doing a proof by contradiction, just doing the proof by contradiction immediately by assuming this is false. So I can get us started there. How would that look? Well, just like the previous problem, it would become there exists x comma y in the integers. So I'm assuming that this thing is false, which means I'm assuming the negation is true. Let me write that here. Negation true. And here's the negation, that there exists an x and y in the integers such that, and then I'm negating the if then by negating the conclusion of the if then. So, except I'm writing it without the if then anymore. So such that x and y are odd and there does exist an integer z such that this happens. Now this is not really going to change your proof at all, if you notice. So when you do the proof by contradiction, what you're doing is you're going to be assuming all of this. So just take this, copy, paste it right there. Assume that there does exist an x and y in the integers such that they're odd and that there exists an integer z such that this happens. That's exactly what we did here, except I used the word let. But it's the same. So then the rest of the proof will be the same. All I'm doing is using different logical equivalences secretly without saying them, partly because I don't want it to get too confusing if I overly worry about that stuff instead of just doing things. But what's going on here is that if I say that not P implies Q, that's equivalent to P and not Q. So that was a thing we did a long time ago. I hope I'm remembering it right, otherwise I'll have to make a correction after. But that's what we're doing here. We're saying that when we're negating this for all statement here, this for all if then statement, what we're doing is we're saying that the for all is becoming that there exists, and then I'm negating the if then by turning it into an and. So I'm saying that P happens, that's P, X and Y are odd, and the negation of Q happens instead of writing it as an if then. It becomes an and when I negate it. So that's two different ways of doing this proof, but the proof itself is really the same. If you really read these two statements, they're the same. So you can think about it as I'm assuming that there exists two integers doing this thing such that, sorry, I'm assuming that there exists integers that are odd and that there's a third integer that makes this equation work, or over here, I'm letting two integers exist and assuming a third integer exists doing this thing. But then the rest of the proof will be the same. So this is why I prefer trying to convert it to an if then immediately and just thinking about it this way. But either way is fine. It's the same thing. Okay, so that's it for this lecture. See you next time.